In Chapter 1, we talked about ways to collect data, and in Chapter 2, we talked about how to take good and bad samples, good sampling methods and bad sampling methods. In Chapter 3, called What Do Samples Tell Us?, we're going to finally start thinking about what we do with the data once we get it. Some definitions first. A parameter is a number that describes the population. A parameter is a fixed number, but in practice we don't know its value. A statistic is a number that describes the sample. Notice the alliteration here: parameter, population, statistic, sample. The P's go together and the S's go together. The value of a statistic is known when we have taken a sample, but it can change from sample to sample. We often use a statistic to estimate an unknown parameter. There's a lot of information in this little section. First, you need to know that the parameter is the number that describes the population, and then you need to know that the parameter is fixed and we don't know its value. The statistic describes the sample, and you also need to know that the statistic is known, so we do know it, unlike the parameter, but it's not fixed. It can change from sample to sample. Think about it this way. Let's go back to our made-up study, where we said we wanted to study the average weight of a USC student. The population there would be all USC students. The parameter, the number that describes the population, would be the average weight of all USC students. The sample might be 100 randomly selected USC students. And then the statistic, the number that describes that sample, would be the average weight of the 100 randomly selected USC students. Now the parameter is the average weight of all USC students. That is a number. If we could part the heavens and look down, we might be able to know its value. In practice, we don't ever know its value. But it is a number. I hope you can all agree with me that at this moment in time, it is a fixed number. But you also understand we don't know its value. However, that's why we look at a sample. The average weight of the 100 randomly selected USC students in our sample, the statistic, that number is known. We observe it. We see what it is. But if I was to get another sample of 100 USC students, do you think the value of the statistic, that is the average weight of the next 100 USC students, is going to be exactly identical to the average weight of the first 100 USC students? No. This is due to something called sampling variability. We understand this is there, and we have to account for it. But the only point that we're trying to illustrate right now is for you to understand that that statistic is going to change from sample to sample. We often use a statistic to estimate an unknown parameter. For those of you who like to visualize what we're talking about, imagine this population of light bulbs. We're going to select a sample, maybe 5 light bulbs. This happens all the time in industry. When we're inspecting lots, we can't sample all of the light bulbs in the lot or we'll ruin the whole lot. We might be sampling lifetimes for the light bulbs or how break resistant they are. So we take a sample of 5 light bulbs and then we're going to calculate the statistic based upon the sample. That might be the average lifetime of those 5 light bulbs. And we're going to use that as an estimate of the average lifetime of the entire lot. The average lifetime of the entire lot would be our parameter. Let's do an example. Voter registration records show that 18% of all voters in Philly are registered as Republicans. However, a radio talk show host in Philadelphia found that of 20 local residents who called the show recently, 60% were Republicans. We need to pick out the population, the parameter, the sample, and the statistic. So we're studying the percent of voters that are Republicans. The population of interest, then, is all voters in Philadelphia. The sample is the 20 local residents who called the show. Now the statistic is a number that the radio talk show host knows because he took the poll. So what's the statistic here? What's the number that describes the sample? Of the 20 local residents who called the show recently, 60% were registered Republicans. So 60% is the actual value of our statistic, and if we write it in words, it's the percent of the sample registered Republican. How about the parameter? Remember we said usually we don't know the value of a parameter? Well, this radio talk show host didn't, but we happen to have access to the voter registration records, so we actually know the value this time, which is rare. We know that 18% is the percent of all Philadelphia residents who are registered Republican. Our next example is from a Pew Research poll conducted September the 26th of 2012. A record 1 in 5 households owe student loan debt. The article estimates that 19% of the nation's households, based upon polling 6,500 households, owed student loan debt in 2010. And just a little fact for you, this is twice the percentage from 2 decades prior. Again, we're going to choose the population, the parameter, the sample, and the statistic. Who did we call in our poll? We polled households. So our sample is the 6,500 households in the poll. The population then is all households. So now the parameter is the number that describes the population, and the statistic is the number that describes the sample. Now, Pew Research couldn't get a hold of all the households in the United States, so they used the numbers that they got from the 6,500 households that were in their sample to estimate that 19% of the nation's households owed student loan debt. So the statistic is 19%. And again, that's the percent of the sample who owe student loan debt. The parameter is the number that describes the population, and here we don't have any way of finding out what percent of all households owe student loan debt. This polling company doesn't have access to that information. The parameter, we don't know the actual value, but it is the percent of all households that owe student loan debt. And we don't know its actual value. That's the thing we're trying to estimate. Now we're going to talk about a specific parameter and a specific statistic. We're going to use p hat to estimate p. P hat is this symbol right here. It's the letter P with the little caret sign on top. And in statistics, we call that thing a hat. P hat is the sample proportion who have the trait or opinion of interest. P hat estimates P. So P is the population proportion who have the trait or opinion of interest. So in our made-up example earlier when we were trying to estimate the average weight of a USC student, our statistic was the sample average and our parameter was the population average. Here, we're talking about a sample percent or sample proportion versus a population percent or population proportion. Example 3. Suppose a Columbia-based health club wants to estimate the proportion of Columbia residents who enjoy running. Let P be the proportion of all Columbia residents who enjoy running. We decide to take a simple random sample of N equals 100 Columbia residents. P hat is going to be the proportion of the sample who enjoy running. After taking the poll, it's discovered that 17 of the 100 Columbia residents said that they enjoy running. The sample proportion is then 17 who said yes. In fact, let's accentuate. That is the number who said yes divided by the sample size. 17 said they enjoyed running out of the 100 people in our poll. And if you punch that in your calculator, it comes out to be 0.17. And a lot of us like thinking in terms of percentages. Moving the decimal places over 2 places to the right, it comes out to be 17%. Suppose now that we take another simple random sample of Columbia residents of size 100, and this time 22 of them said that they enjoy running. Then the sample proportion would be 22 over 100, which is 0.22, which equates to 22%. As we can see, this is a relatively realistic example because we do not expect to get the exact same percentage of each sample that says, yes, we like to run. We understand in our guts already that there is this notion of sampling variability. Each sample is going to look a little bit different than every other sample. So once we notice that we have two samples from the same population and the sample proportions are different from each other, we can ask some questions. Are statistics from different samples going to be exactly the same? No. We are not going to expect them to be exactly the same. Is our statistic calculated from any one sample going to exactly match the population parameter it's trying to estimate? No. Probably not. Therein lies the problem. The fact that our statistics will not be the same from sample to sample is called sampling variability. We'll use this term all throughout the semester. But we hope that as long as we have a good sampling scheme, we'll be estimating the population parameter fairly well when we take our one shot at estimating it. Some terms to learn before we examine this notion of sampling variability. Here comes that term bias again. Bias is consistent, repeated deviation of the statistic from the parameter in the same direction when we take many samples. Variability describes how spread out the values of the statistic are when we take many samples. That is, if I take 10 samples of N equals 100 and poll our Columbia residents about whether they enjoy running or not, is my sample statistic, is that percentage going to swing wildly from sample to sample, which would mean large variability, or is it going to stay pretty close to the very first estimate? That is, does that estimate have small variability? Our goal is to obtain both small bias and small variability, and a good sampling scheme will have both, although we'll have different strategies for correcting for these. Let's talk about bias and variability in a setting that hopefully all of you have encountered at some point in your lives. Let's look at these bullseyes. Hopefully everyone's played darts at least once or shot at the range at one point in their life. So you can imagine a bullseye. In the top left picture, over here, what are we seeing? Are these darts hitting the center, or are they off in the same direction every time they throw? These are off in the same direction every time we throw. This picture is showing a large bias. However, is it pretty predictable where this person's going to throw their darts? I would say so. It's pretty consistent. So here, we would call this small variability. In the top right-hand picture, are the darts on average hitting the target? Some are to the left, some are to the right, some are too high, some are too low. But on average, are they centered around our target? Yes, they are. So here, we're showing low bias. However, are these darts predictable, or are they really spread out? They're really spread out. So we're going to say this has high variability. Now the picture in the lower left-hand corner has high bias because on average these darts are off the mark. They're all too high and to the right in general. They're also unpredictable. They're really spread out. So we're going to say this has high variability. And in the lower right-hand target, this one's got low bias. The darts are centered around where they're supposed to be hitting, and also low variability. Now, how would you correct for the top left picture? That would be easy to correct. All you do is aim a little bit to the left and down. The ones with high variability are a little bit harder for us to fix. They have a different strategy for us to fix. So bias and variability are two very different types of errors when we're using statistics to estimate parameters. We talked about the notion of sampling variability. That is, a statistic is going to vary from sample to sample, because we know that each sample is a little bit different from every other sample, even though they're drawn from the same population. In these two pictures, we are exploring sampling variability. Now this is going to take a little bit of a stretch at first. You may have to watch this portion of the video a few times, but bear with me for just a moment. Let's try to understand what we're looking at here. We have a population with some characteristic that arrives in a proportion of 0.6, or 60% of the population has this. Let's make something concrete up. Let's say that 60% of this population has brown eyes. If I were to take a simple random sample of n equals 100, I could get a p-hat that has 56% of the sample having brown eyes. But we know there's sampling variability. If I take another sample, this might change. So if I take another sample of 100, I could get a p-hat that's even lower, 46%. Could take another sample and I could get 61%, and so on and so on and so on. If I do this 1,000 times, I might get a graphic that looks like this when I'm trying to think about where p-hat falls most of the time. Let's explore what this graphic means. It's called a histogram. And let's take, for instance, this bar, this bin right here. This bin on this x-axis for the values of p-hat goes from 60% to 62%. And the height of the bin, the height of the bar, is roughly 150. And that means that 150 of our samples had a p-hat between 60 and 62%. So as you can see, the taller bins mean that the p-hats landed there more often. We rarely, the short bin out here, had a p-hat above 70%, and we rarely had a p-hat below 50%. So we kind of get an idea of the distribution. Now let's picture the same scenario in the bottom set of graphics. The same population, where 60% have brown eyes. But this time, we're taking a simple random sample of 1,523 people instead of 100. So now we take our first sample of size 1,523, and we get a p-hat of about 61%, 0.609, which is 60.9%, which I'm rounding up to 61. Our second sample results in a p-hat of 62.5%, And our third one results in a sample with 57.9% having brown eyes. And we could do this 1,000 times, taking these larger samples each time. Now look at the histogram. We can see that there's nobody down here in the 50%, and there's nobody up here above 65%. There were, however, in the distribution when we had samples of size 100. So what can we say? What can we kind of start to infer from these pictures with the larger sample sizes versus the smaller? Well, it looks like the p-hats are still centered around the true value of 60%. 60% is in the center here, and 60% is in the center of the values up here. However, so that doesn't change according to our sample size. However, it looks like the p-hats are less variable. They swing less from sample to sample when we have the bigger sample sizes, because this histogram is more narrow. It doesn't have extreme values in it. So what do we want to take home from this? P-hat is an unbiased estimator of P. And this does not depend on sample size. However, p-hat has more variability. That is, the estimate swings more from sample to sample with smaller sample sizes. And vice versa. So p-hat has less variability with bigger sample sizes. And these will be facts that we will be visiting all semester. Bias has nothing to do with sample size, but variability has everything to do with sample size. The higher the sample size, the lower the variability. To reduce bias, you need to check and make sure that you have the best random sampling scheme possible. This does not have anything to do with sample size. If I ask you how to reduce bias, you should always talk about other things other than sample size. To reduce variability, get a bigger sample size. You can make the variability as small as you want by taking a large enough sample size. Large random samples almost always give an estimate that's close to the truth.